Hello all, welcome to the video lecture series for the subject compiler design. Now I'm going to explain you all about the principal source of optimization, right? So this is the one of the techniques which is adopted in optimization, which can be done globally or locally, right? In the previous lecture I was explaining about the basics of optimization, when there is an optimization is required, why the optimization is required, if anything happens, anything do in optimization, and what are all the other facts which should not affect the optimization technique we have seen, right? So let me take you to the basics of optimization, the principal sources of optimization that is the most important and globally used, right? So in this part, let me explain you about the first basic part of it, that is compile time evolution. So this is the first important fact of principal source of optimization, right? What does the compile time evolution does? Okay, I will explain you with example. Basically, this compile time evolution is used for shifting a computation from runtime to compile time, right? So this particular part can be done by using a technique called folding, right? So what is a folding? Basically, folding is a compile time instead of execution time. Say for example, one example I can give for this. Say for example, length length is equal to 22 divided by 7 into d, right? So the basic formula here, length is equal to pi into 3.4 into d, or else pi into d. So here, instead of 3.4, the value has been folded, right? So this is the basic part of how does the folding works. It is used instead of compile time, execution time process has been taken to produce this point, that is divide 22 divided by 7, that is 3.14. We used to call it as pi value, right? So here it is, the process. Second example I can tell you here, in this compile time evolution, we have a constant propagation, right? So that is the second basic thing, constant propagation, right? What is constant propagation? It's very simple. Actually, the constant propagation takes a value of a variable. Here, you can see that it takes the value of the variable, and the variable is replaced and computation done at the compile time. Okay, so what best example I can give here, it is pi is equal to, that is pi value 3.14, right? So this is the pi value you can get, and I'm having initializing value r is equal to 5. So I'm asking you to find what is the area. Area is equal to pi r square, you all know that, right? Pi r square. So if I define this pi instead of this is the actual formula. Instead of this formula, the value is already there. So the point is, the variables are replaced and computation done at compilation time itself. Here itself the value will be expressed, and the process has been done immediately, not in the execution time, it is done in the compilation time. So you can see here the value here, it is already there. So area, forget about this is the formula. So area is equal to pi into r into r. So here the value is already there, so it takes the compilation process, that is compilation time, to done a process of it, right, instead of execution time. That is the best example I can tell you, right? So I can take you to the second best example, or else I can take you to the second principal source of optimization. It's very simple. So I can call it as common sub expression elimination, right? This is also a very important process, where you can see that this process, you can see that it is used to eliminate any number of lines. The code doesn't have any redundancy, it can always look for redundancy also. So here, in order to eliminate the repeated lines, say for example, so whatever I'm explaining, I used to call with example so that it is best understanding for you people. Say for example, there is a three address code, T1 is equal to 4 asterisk I, right? T2 is equal to A of T1. So whatever I am doing here, this is for an example. You can check it. If any process here, any expression here is written with error, don't bother about. This is for an expression elimination, right? So we are going to check the redundancy. So T3 is equal to 4 asterisk j, for example, right? T4 is equal to 4 asterisk I. Okay. So this may be a human error. Why? Because you can see T1 is 4 asterisk I. Again, T4 is equal to 4 asterisk I. This is temporary term is different and this temporary term is different. Right. So T5 is equal to N. So finally, T6 is equal to, right, B of T4 plus T5. Now you can check which particular line is not called or else which particular line is useless, right? Now for this particular thing, I need to write an optimized code, right? I need to write a optimized code for this. What is the optimized code? Very simple. So I am going to take the redundancy part out from this particular way, right? Which one is the redundant part? This is, right? If you don't want to disturb a code, you can write like this. Say for example, T1 is equal to, for example, T1 is equal to 4 asterisk I. This is a point number 1. T2 is equal to A of T1, right? The code, whatever the optimization, I was explaining the same thing in the previous video also. Whatever you do, that should not affect the process, like the process in the sense the original code, right? So T3 is equal to 4 asterisk J. You can check simultaneously whichever the line I was exactly finding out where there is a redundancy, right? So here T5 is equal to N. Okay, so here T6 is equal to B of T1 plus T5. I hope you understand. Now this doesn't make any difference. Why? Because T1 is equal to 4 asterisk I. T4 is also 4 asterisk I. T1 is computed in the second line, but T4 is not computed any of the line other than this T6. So I have exactly removed this redundant particular line and I replace that by the same value 4 asterisk I. Instead of 4 asterisk I in T4, I call here it as T1. So I can call this as an optimized code. This is a non-optimized code. This technique we used to call it as common sub-expression elimination. Okay, so let me take you to the third important part of principal sources of optimization. So the point here, it is variable propagation, or else we can call it as copy propagation also, right? So you can call it as variable propagation, or else you can get lost, or you can call it as copy propagation. So what exactly it does? So let me tell you with example, right? It is used for one variable instead of another. Okay, so what example? That is usually we used to call it as copy propagation. Okay, so for example, with example you can see how exactly this copy propagation works. For example, x is equal to pi. Okay, so now area is equal to x into r into r, that is pi r square. You know well what is the formula for area, right? Now I can say this is not an optimized code. Okay sir, so can you write what is the optimized code? Exactly. So instead of this x, right, the pi value is stored in x. Again the x has to be open and it will find what is pi, and the pi value will be 3.14. It takes much time, nanoseconds, other than the optimized code. So this can be actually copy propagated. Say for example, the optimized code can be in this form. Say for example, area is equal to, instead of x, I can call the value called pi directly, pi into r into r. So this is a optimized code where the variable propagation is exactly working, right? So here you can see that instead of the use of one variable instead of another, I can use this variable instead of x. So this is how the copy propagation works. Okay, So let me take you to the fourth approach in principal source of optimization. The process here you can call it as code movement, right? This code you can write in, you can do that code, this particular example, in any of the language, whichever the language you are comfortable in, right? So let me tell you what is this code movement. Okay, what is this code movement? It is to reduce the size of the code. Okay, number one, size is reduced. Okay, the size has to be reduced and it should not affect the original code. They should be always, right? It should reduce the size of the code with space complexity, best space consequency, right? Reduce the frequency of execution of code. Okay, that is time complexity. So we need to always, you can see, first is size has been reduced. Second thing is we can say frequency is reduced. Okay, and we can call this is for space complexity. This is for space complexity, and here I am calling it as time complexity. Why? Because the size is reduced, so we can call it as space. The frequency reduced, then it should be definitely time. Right, sir, all okay. So we can go with one example so that you will understand how the space and time complexity is really works. Okay, one best example I will call for code movement. Right, what is a code movement? Basically, I told you already, it always focus towards this two. For example, I will take this for loop. Okay, so this is f. Okay, case sensitive. I is equal to 0, I is less than or equal to 10, I plus plus. Okay, so now x is equal to, for example, I'm writing it, this is for computation, you can take any of this. K is equal to y asterisk 5 plus 50, and I'm going to close this. Okay, now listen, this is the code has been given to you, and they are asking you for write the optimized code. That is, you can use this code movement, this particular approach in principal source of optimization, and you need to optimize this. Okay, let me write the optimized code for this. Right, so I need to move something out, so that is actually the code movement. Say for example, whichever the value which is repeated here, I can say this value can be moved out. Okay, so I'm declaring it globally. Say for example, I mean z is equal to y asterisk 5. Okay, so now write the for loop for I is equal to 0, I is less than or equal to 10. I am not changing the actual structure of the code. Whatever is there, I am just taking it. I am not changing anything. So this is how it is. So here x is equal to y asterisk 5. So we moved that y asterisk 5 here. This value has been assigned to z. So x is equal to z. So this is the point. Now how to write this particular thing? Say you should not change whatever is there in the previous code, and it should not change in the next process. So x is equal to z. So what to write in this particular thing? K is equal to, you write the same z value, z plus 50. Now this code, this particular, compare this code. See here, instead of y asterisk 5, the value has been initiated as z. So what is z? Y asterisk 5. It was declared globally. So that's the process. So we need to be very specific about optimization code, but it should not always change the regular structure of the user. Right? Why? Because this optimization is not happening in the front end. That means it is not happening in the analysis phase. It is happening only in the synthesis phase, that is back end. So there is no knowledge about the user, what exactly the optimization is working with. So we need to, this compiler will be very particular about it. It will not change the structure of the code. So this is what all about code movement. Right. So this is the fifth approach in principal source of optimization. The name is loop invariant computation. This is the most important technique. What is this loop invariant computation? Moving some amount of code outside the loop, like we did in the previous approach, and this is little change. We can see the code movement is different, and we can see amount of code outside the loop is different, right? So here, previously we didn't do anything in the loop, right? For example, you can take it in this way, that is while. So for example, I'm taking the conditional open. I is less than or equal to max minus 1, for example, and sum is equal to sum plus the value a of I, and it has been closed. Just focus only on this particular part because I cannot write the full code. Okay, so the a is already there, you know, the I has been already initialized. Now sum is equal to sum plus a of I. Now the loop is invariant here, you can check it. I is less than or equal to max minus 1. Whenever the value, whatever the value of maximum, that will be always minus 1, and that value will be compared with I. It takes little time. So what this optimized code does here, how does the code can be written in optimized form? Now say for example, moving the loop has to be done, the amount of code in the loop has moved outside, so n is equal to max minus 1. So you are moving this out. Now you can write this while loop, while I is less than or equal to n. Now you can see that n value will have a computed answer, so that it will always check, it will don't do this. Okay, so now you write the same process, whatever is there up in the code, you can just check it. Sum is equal to sum plus a of I. So sum is equal to sum plus a of I. Now the value, you can see that I am going to close the code. So this is going to be a optimized code. This is a optimized one. Right? So in the same future, we have one more approach. We can call it as strength reduction. Right? Right, in strength reduction, you can see that it is going to reduce the strength of the technique. Okay, it is going to reduce, it is always going to follow the reduction technique. Okay, higher strength operator can be replaced with the lowest strength, that's it. Okay, okay, highest strength, whichever the highest strength, that is asterisk, can be converted into plus or minus or whatever it is. Okay, so the highest strength operator is reduced here. Example, I can write one example for this. For I is equal to 1, okay, and I is less than or equal to 50, I plus plus, right? So here count is equal to I asterisk 7, and it was closed. Now you are asked to optimize this code. That means you need to reduce the strength of it. So where you can do, you can take and you can see only this part of the code you need to check, and you need to reduce the code. Okay, so what exactly you can do? So you should not change the structure, that's the point, right? So the line is simple here, but the strength is high, so you can write the optimized code. So what I'm going to do is I'm just going to take this out, that is temp is equal to 7, the value temp is equal to 7. I'm going to bring down the same for loop here. For I is equal to 1, I is less than or equal to 50, and I plus plus. Okay, so now you can check it. Now what I'm going to do is I'm going to have this count is equal to temp. Okay, so what is temp now? Temp is 7. Okay, I will write the last two lines here. So this is line number 1, line number 2, line number 3, this is line number 4. Count is equal to temp. Now count, the value of temp is 7, 7 is loaded here. So I am going to increment this temp now. Okay, how to increment this temp? Temp is equal to temp plus 7. So I am going to close it. I can full confidently say that this strength has been reduced here. How? So here the I asterisk 7, instead of that count is equal to 7, temp is equal to temp plus 7. So initially temp is 7, and after that the value of temp is 14. Now it is 14, again it will go and print, again count is equal to temp. Now the 7 will become 14 here. Temp is equal to temp plus 7, that is 14 plus 7 is equal to 21. Now this will become 21. So it will keep on printing the same value unless I is less than or equal to 50. So 50 times it will take and produce the 7th multiply value. Got it? So this is how I is initially 1 here. I will become incremented by 2, incremented by 1, again 2 into 7 14, Again it will 3 into 7 21. So it will keep on do it. Instead of asterisk, I did the same process by using this plus. Okay, so the final phases, final technique which is adopted in principal source of optimization, that is dead code elimination. Okay, so I will write the code here. You can check it, which code can be, or else you can say which code can be a dead code and how to eliminate that particular code. Now, I is equal to j, okay, x is equal to I plus 10. So you see this code, whether this code, this particular code will reach here. I is equal to j. We don't know what is j. So whenever we are going to have this initialization, that x is equal to I plus 10. This we can call it as a dead code. One example, because this code, this particular line will never reach to the second line. This is one example I can tell. Next, one more example if you want, like I is equal to 0, so that you will get the more with the loop. I will explain this. If I is equal to 1, okay, so I am going to check. See here, I have been initialized. I am, no increment has been done. Directly I am checking it. If I is equal to 1, this code will never reach here. If I is equal to 1, I am going to have this expression, a is equal to x plus 5, something like that, and close it. Now you check it and see how exactly this happened, whether this code will reach the next line. No, there is a big question mark here. Whether this code will reach here? No. Whether this code will reach here? Definitely not. So we can call it as dead code elimination. Now this second part, that is synthesis phase, will look, that is code optimization, look for this dead code also. If it finds anything in the dead code, then it has to be eliminated immediately. So this code has been eliminated, this code has to be eliminated. This is how the principal source of optimization is working with the input. That is, the input whichever it takes, that code has to be optimized code. Thank you.